So I put here. Yeah. am Jay Chen from UMass Boston, and this is joint work with Elisa, and she is a former graduate student supported by U54. This is our joint work on using spatial scan statistics for the detection of the spatial clustering of the breast cancer by using Massachusetts cancer nugget data. And in the first part of this talk, I would like to discuss a general statistic framework of statistics and the spatial scan statistic. In the second part, I will present the applications of the spatial scan statistics, especially using the a free statistic software StatScan for the spatial data detections for the breast cancer data. And that's for the second part here. Okay, so our objective for this talk is to find out a specific cluster location by using two-dimensional scan statistics. I will begin the introduction of the one-dimensional scan statistics with extension to the two-dimensional scan statistics and variable window scan statistics. I will especially focus on the cutoff spatial scan statistic by using StatScan software here. So for the application of the Massachusetts cancer nugget data for the cancer incidence is the number of the diagnostic cancer account happened in a specific population during the year period. Okay, so usually it is counted per 100,000 of the population at risk. So we like to report and to evaluate the spatial clustering for certain type of cancer disease. So for this talk, it will be breast cancer and on the distribution of Massachusetts. And for this study, we'll aggregate the data on the counties and then by the census tracts. Okay, so here is the introduction of the scan statistic. Okay, so we begin with the one-dimensional case. That a 0 to t be a time interval, for example, from the time 0 to up to time of the t is a continuous time interval. Over this time period, there are a total number of the n events will happen. So under the null hypothesis, those n events is supposed to be randomly distributed over entire time period. And under the alternative hypothesis, it is assumed in certain time interval there is increasing of the intensities. Okay. Now, how do we do that? How do we test it? There is increasing of the intensities. And we propose to use the one-dimensional scan statistic with a moving window of the length W here. In the beginning, we start with a fixed length of the moving window of the W. So in this picture, we slice or scans a length of the moving window W from the beginning up to the end. Okay, and so we try to detect in certain time interval that is highest the number of the events. So the null hypothesis is randomly distributed, and then the alternative hypothesis is here, begin with a certain time point, for example, from t0 and with the interval of the W, there is increasing number of the events there. Okay. Now, this is the scan statistic is defined as the maximum number of the events over the time interval from 0 to t here. Now, if we know the distribution of the scan statistic, whenever we observe the number of the events in a length of W, we should be able to calculate the tail distribution of the scan statistics. Okay. However, there's no exact distribution for the scan statistic due to high dependency of the events. So, we use a very accurate approximation to calculate the tail probability of the scan statistics. Okay, so there are two types of the approximations of for the distribution of the tail probability of the scan statistic. Okay. Now, if the window size is fixed, for example, the W is fixed, and we know the clustering size is W. So in that case, the scan statistic, okay, which is the maximum number of the events in a certain window, which is the maximum likelihood ratio test. Okay, so this has been approved in a Knauss early paper, 1966. However, if the clustering size is unknown, and to use a fixed window of the scan statistic may lose of the sum of the power here. Okay, so in the past few decades, there are many researchers have been studying of the variable window scan statistics. And for this seminar, we'll concentrate on three types of the variable window scan statistics. One is the cutoff type scan statistics, and then minimum p-value variable scan statistics. And the third type of the variable window scan statistic will be Bayesian type of the scan statistics. We'll try to use those three types of the variable window scan statistic and to test the randomness with the clusterings for the time interval and then for the spatial clustering for the two-dimensional case in the study. For the study area is the map, for example, here. Okay. Now, if the window size is unknown, so as I mentioned that if I use the fixed, scanning window and then the size is not accurate, so in that case, the test will lose power. So instead, we propose to use a sequence of the moving windows. The size, okay, varies, for example, from 1 to n, so a sequence of the moving windows. And then for each size of the scanning window, okay, we're scanning the window from, from the beginning, time 0 to up to time t, we scan the window, and we try to find out the maximum number of the events, okay. Now, and then we denote this so-called observed, okay, this so-called observed maximum number, so-called observed scan statistic, okay. Now, with this observed number, we should be able to calculate the tail distribution by using the approximations and using this formula. And Wilson and the Neff 1987's approximation, or to use the very famous Q2, Q3's product type approximations in Knauss 82. So we should be able to calculate all those a sequence of the p-values. Okay. Now, for the minimum p-value, variable window scan statistics is defined as the minimum number of those p-values. Okay. So we should be, with a given data, we should be able to find out and observe the p-mean test statistic. However, there's no distribution formulas for the p-mean test statistic. So in that case, the significant level should be evaluated based on the simulation, which means under the hypothesis with n number of observations, we randomly assign those n numbers across entire interval from 0 to t, and we're scanning all, the sequence of the window and to calculate the p-values for each of the moving window, and then to calculate p-mean test statistic. And we repeat this calculation, based on number of the trials, like, number of the simulations. And usually we use 10,000 number of the simulations. And then, the p-value actually is the percentile or the order of the observed p-mean test statistic. So that's the way to evaluate the significant level. If this p-mean test statistic is significant, which means, the p-value less than 5%, and then we say, yes, there is clustering of the event happened in certain interval, and then we should be able to locate the, the location of the interval and then the length of the intervals. And I will give an example to show how to find out the location and then the length of the interval. And I would also like to, to introduce the generalized likelihood ratio test. Okay, so if you look at this formula, this is very familiar. This is very similar to the cutoff spatial, scale statistic. Actually, this is the early version of the, cutoffs and the spatial scale statistics. In his early paper, 1995, there are two articles here, all by Statistic in Medicine. And one is for the one-dimensional case, is the formula, this here. The other is for the two-dimensional case in 1995's paper, but they are very similar, test statistic based on generalized likelihood ratio test here. And here, again, there's no distribution available for the generalized likelihood ratio test statistic. And then the p-value is also evaluated based on the simulation approach. Now, the third type of the variable window scan statistics is kind of Bayesian type scan statistics, which is based on an estimate of the base factor there by using two-stage hierarchical prior approach here. Okay, I'm not going to go those details of those mathematical formula and the derivation, but here we can use the Gibbs sampling to drop those random sample and then to calculate the observed base factor, and then also based on the simulation to find out the p-values for the test statistic of the base factor here. Okay. Now, I would like to present an example to show how can we use those variable window scan statistics to find out the clusterings. Here is a data set with 35 cases of the birth defect, okay, over the 6 years time period. Actually, and there are a total number of the 2,191 days. So we arrange those, actually, these are observed. These are real data, so they are observed 35 cases, which is distributed in the time interval. We can set from 0 to 2,191 here. Okay, so they are all days here. So, and the first column with are the days where the event happened. Now, the first case happened on June 19 of the 1951, which is the 170 days from the beginning. So the day is 170, okay, 170 days from the beginning. And then the next event happened on November 12, 1950. So the gap between those two events, so the length of those two events was 146 days. And then after another 129 days, and then the event happened again, which is on March 21st, 1951. Okay, so there are a total of 35 cases happened in the time interval from 0 to 2191 days here. Now, if you look at those numbers here, okay, so if you look at those numbers here, those are very small lengths, okay, so which means those, during those days, the events seem like quite, clustering distributed, okay. So here, for example, was the June 2nd, 1953, and then June 3rd. Okay, so 1 day later, there's another event happened. And 3 days later, on June 6th, 1953, another event happened. And then 7 days later and 8 days later. So those, if this number are small, the length of the event happened are smaller, which means it could be more crowded or more clustering of the events will happen here. Okay, so if I make the plot of this data here, so you will see that those are zeros, those are ones, which means the days of the event happen. So in those time period, okay, the events are more likely to be clustering together in those time period, okay? But this just by guessing. So we need to use test statistic to find out where the location and the length of the, the windows or the length of the days where the events are most likely to be clustered. Okay. Now, first of all, I use the generalized likelihood ratio test, use the previous formula, and use this formula to do that. Yeah, generalized likelihood ratio test. Okay, so in that case, with the observed data, okay, with the given data, we found the maximum likelihood ratio test, the lambda, was this number, okay, was very big number there, 43.968. And then we should be able to find out the location of the first event happened here. So the most likely cluster was happened on the days of the, 1233, which is from the day of the, which with the 15 cases and about 259 days there, okay? So if I go back to the table here, so you should be able to find out approximate the days that will happen here. So that's, so it's about in this area. So see that. So it starts from the, the May 17 of 1953, and then for the, it's about the length of the 259 days, and there are about 15 cases will happen. Remember, the total cases were 35, so there are clustering happened in this time period, okay? And then observe the p-value, we should be able to calculate that based on the simulation, which is less than 5%, which is significant, okay? But if I use the, p-mean test statistic, and which means we're going to slide the window, find out the maximum number of the events, and then calculate, use the approximation to calculate p-value, and then find the p-mean value, the minimum of the p-value. We found that the minimum of the p-value happened, which is exactly in the same day. It's the t equal to 1233, with the length, slightly difference of the, the length of the window is about 263 days. And we calculate the p-mean test statistic, which is about 3%. So here, the observed scan statistic, observed the largest number, which we found is also 15, and then the p-value is also small. We find that the p-value is also small, which is also significant. Yes, okay. And if I use the Bayesian variable window scan statistic, first of all, I will use the moment method to estimate those priors. And then with those priors, we can give sampling and then to, find out the maximum number of the base factor, which is happening in the same day with the same length and with a size of the 15 cases. So all those three, and the one-dimensional scan statistics, and give us the same finding as the location and the length of the similar length of the sliding windows here. Okay. now we we use the one-dimensional scan statistic as the introduction, but we like to work on, for this seminar, we like to work with spatial scan statistic, which is the two-dimensional case. So we begin with to define the two-dimensional scan statistic, which is defined as the maximum number of the events in a moving window. Okay, this window could be a square, could be a circle, and then it could happen in any of the locations. Okay, it can happen in any of the locations. Okay. Again, the distribution of the scan statistic is unknown. Okay, there's no exact formula to calculate. Okay, for the calculation of the tail probability. If there is a formula, and then for any of the observed value in the moving window, we should be able to calculate tail probability. But unfortunately, usually we do not have such of the exact distribution. We also use the approximations for the tail probability of the scan statistic, which is in this quite complicated formula, and it was developed in not an early article in 1991 of Theorem 3.1. For this formula, actually, it's based on the large scale of the deviations, and then the second term here is try to, it's the second order that will improve the significances of the first order of the first term of this formula. So this is only an optimization for the two-dimensional continuous Poisson process. We can use this optimization to calculate approximate distribution of the two-dimensional scan statistic if it's in the rectangular starting area. Okay. Now here is an example to show how those moving sum can be calculated over a unit square. So here, suppose under the null basis of random distribution of the randomness distribution, suppose there are n events. For this example, n is 50. There are n events random distributed over a unit square. So we should be able to use the moving window. Okay, here I only use a fixed moving window in the beginning with the size is 10% of the entire study area here, and try to find out the sum of the events in all these moving windows. Okay, now and you will see that this number is the maximum number of the events in one of the moving window. However, since these are random distributed, so this is not actually based on test. Okay, it's not significantly higher compared to other of the events. Okay, in other of the events there. But under the alternative thesis, there is a clustering here. So in certain area, there is elevated some of the numbers in certain of the moving windows, and then this significantly higher. So this is just an example to show the clustering of the events, okay, which distributed on a unit circle there. Okay. So again, we're not going to use the fixed window scan statistic because we do not know the clustering size. If by mistake we use the different, and the moving window from the real clustering size, the test may lose some power. So in that case, we still need to use the variable window scan statistic. Okay, so for this seminar, I will only present two different types of the variable window scan statistic. I will mainly focus on the cutoff type and variable window scan statistic. The reason is like that, because now the set scan, which is widely used statistic package, was developed by using cutoff type spatial scan statistic. So I'm going to go over quite details of the, how to conduct spatial scan statistic by using the maximum likelihood ratio test using the cutoff approach. I also compare the results with the minimum p-value test statistic. It's the comparison for the power. So you saw this formula before for the one-dimensional scan statistic, and then we extend that to the two-dimensional variable window scan statistic. The only difference is the, the distribution of the scan statistic, and I have to use the different formula to calculate the p-values. Okay. Now, this is the cutoff spatial scan statistic here, and so this formula is based on generalized likelihood ratio test. Okay, so in the cutoff spatial scan statistic, actually, and we have the infinity number of the circles. Okay, but for each of the circle, and it is supposed to calculate, okay, the observed count, which is C, inside of the circle, and then the expected number of the count inside of the circle, and then to calculate, the observed number of the count outside of the circle, and the expected number of the counts outside of the circle. So the cutoff type spatial scan statistic is kind of conditional scan statistic. It's conditioned on total number of the event n is none. So the total number of the events usually is none. Okay. So in that case, okay, so if there are C events happened inside of circle, and then there's n minus C happened outside of the circle here. Okay. So, and the test statistic is generalized likelihood ratio test. So for each of the circle, we calculate this test statistic. Okay. Now, and then for each of the circle, and then we try to find out the maximum number of the such test statistic again, and then use the simulation to find out the p-value. So that's the cutoff type spatial scan statistic. So cutoff type spatial scan statistic assume the count C here is generated by a Poisson distribution with the mean, for example, is the lambda, and so in that case, the counts, okay, the observed counts is proportional to the intensity of the lambda and the population P here. Okay, so it is assumed inside of the circle we have higher intensity of the lambda compared to the intensity outside of the circle. Okay, so here usually the lambda is the disease rate. So under the null hypothesis, okay, so under the null hypothesis, so lambda is equal inside and outside of the circle under the null hypothesis. Okay, so the lambda is supposed to be the same inside and outside of circle. And under the alternative hypothesis, the lambda is higher inside of the circle, which means in the testing area we have higher lambda value. Okay. Now in Carter's paper here, he has showed that this is the most powerful test to find out a local clustering here. He has proved that the generalized likelihood ratio test is the most powerful test of testing the clustering regions there. So so compared to the one-dimensional of the time interval here, and now we extend the results to the two-dimensional spatial case. If this is happened, if the study area is on a map, and then the data can be aggregated by, for example, zip code or the sensor tractors. So for the study area, we move the circle and from any of the center, and then try to find out the maximum number based on this function And then under the hypothesis, okay, we can make it a random sample, for example, 10,000 times, and then to calculate the generalized likelihood ratio test, and then the percentage or the percentile of the observed generalized likelihood ratio test statistic is the p-value. Okay. Now this is the special case of the cutoff spatial scan statistic. This is general case. For the special case of the continued Poisson distribution, which means data are random distributed in a study area. So here, and the expected value is become to the areas, the study area here, okay? So the entire area, for example, for the rectangular region could be the t-square, and then the study area, just the area could be just the square of the size of the moving window here. And then we can also use the circle window, okay? We can also, even, the study region is rectangular, but the moving window could be a circle, could be circles, a sequence of the circles. So the continued Poisson model is to use to test if the events have spatial pattern themselves, or if the events is random distributed over whole study area. So that's the special case of the continued Poisson distribution. Now here is an example. I will use this example, try to compare the testing power with the fixed window scan statistic, variable window scan statistic, with the cutoff type spatial scan statistic here. Okay, now suppose there are 50 cases, okay, random distributed in a study region, and the study region we can always make that into unit square, and then we make a sequence of the moving window, and for each size of the moving window, we can find the observed scan statistic. Okay, with the observed scan statistic, we can find out the tail probability by using approximation, and then the p-mean test statistics. Okay, and then use the similar approach, we can also calculate the power for the generalized likelihood ratio test based on cutoffs approach here. Okay, now the power is calculated under the alternative hypothesis. Okay, so in this example, we assume here U is the clustering size. Okay, with the clustering size, for example, I put the purple color here, with a clustering size in a relatively small area of the 5, this is 5% by 5% here, and with the number of the four cases inside of this study area, and the 46 outside of the study area, we can calculate the power of the test statistic. Okay, now here suppose I use the right size of the moving window. Okay, the same size of the moving window is the clustering size here. You can find out that we have the highest power. Okay, we have the highest power of the test statistic. But unfortunately, if I use the wrong size of the moving window, those testing power are relatively low here. Okay, so instead, I would rather to use a sequence of the moving windows. Okay, so that's a sequence of the moving window here to find out the p-mean test statistic, and then to calculate the power of the p-mean test statistic. So this power is quite good. Okay, 60% and 60% of the power for the p-mean test statistic. Okay, now if I use the generalized likelihood ratio test statistic, okay, and then to compare the observed events inside of square and with the expected number of the events, and then outside of the testing area, we can calculate the power based on cutoff type spatial scan statistic, and then the power is also quite good here. Okay. So in that case, which means yes, if we know exactly the clustering size, we can use fixed window scan statistic. Otherwise, we'd rather propose to use the variable window scan statistics. Now here is a real example. That was the simulation example to compare of the power. Now here I like to present a real data, which is the longleaf pine tree distributed in the 200 meters area here. Okay. Now our research question is: do the spatial location appear to be complete spatial random, or they are clustered? There is clustered in somewhere. Okay, so if I do the plot of the data here, we find there is kind of clustering in this area. Okay, there could be some clustering in this area, but we need to test that. We need to calculate test statistic, and then we also need to conduct the significant level of the p-values here. Okay. Now to use the variable window p-mean test statistic, okay, we also use a sequence of the moving window, okay. For each of the moving window, we find the observed, scan statistic, which is the largest number of the events in a moving window, and then calculate the p-value. Now over a whole sequence of almost like 200 of the moving windows here, and we find out the p-mean test statistic. And then using the simulation to find out the p-value, which is small. This p-mean test statistic was calculated as very small value, and we also use the simulation under the hypothesis to calculate, about 10,000 times, 10,000 times of the p-mean values, and we found that this p-value was significantly low compared to the, all the 10,000 p-values, which is about in the 1% node there. Okay, so we find the area which with the size of the window is about 17%, here, and with number of the cases in the square window is about 10. Okay, now here the expected value actually, okay, now the observed value was found as 10. Okay, now what's the expected number of the value in the moving window of the size about 18 here? So we can calculate the expected value is about like 0.87. So in that case, the observed value of the scan statistic compared, or just observed count compared to expected counts, which is very high here. So the test is quite significant. Okay. Now, yes, I can also use the set scan, okay, by using the continued Poisson data, try to find out the test statistic here, and then we found, okay, there are a number of the, instead of 10 cases, because there are totally two different, approach for the variable window scan statistic. By using set scan, use the maximum likelihood ratio test, we found that there are 7 cases in about the same region with the significant height, significant lower of the p-values, and then the log likelihood ratio test statistic was about 15. So this was the output from set scan. Okay. So compared to set scan, we can also use the MATLAB program or the R program, and then to conduct those maximum likelihood ratio test statistic. I use that for both square moving window and the circle moving window here. So if I use the circle moving window here, I found exact the same result as set scan if I use a MATLAB okay? If I use the square size of the moving window, and we get similar results, but not exactly the same because this square window, but we get a very similar result. For example, the number of the cases, the number of the clustering cases was 7, and then the log likelihood ratio was about 15. So these are quite same, but the size of the moving window were not the same because one is the square window, the other is circle window. So that's the MATLAB program, so give the almost the same results as the using set scan here. Okay. So most of researchers like to use Spatial like set scan because it is a free software and it's easy to use. Okay. Now the native version, which is 9.6, okay, which was developed last year, 2018 in March. Okay. This is a website, and if you have chance to visit the website, there are many of the articles and the data sets available as example to learn the set scan, and then you can try of the their existing data sets with map data sets to generate the spatial scan statistic in a map here. Okay. So that's the website of the scan statistics. Okay. So for the set scan, actually, you will need to have input of the XY location, and then we also need to know the number of the cases. Okay. Now, and that's the number of cases for Poisson model. If I use a Bernoulli model, we also need to know the control cases there, cases and the control, and then the population size, the population, all the expected counts, here. And then we can also, input the time interval there. Okay, we can use the time interval as day, month, or year. And then we can define the study period, or we can use entire data sets for all the years. Okay. Now the output by the set scan. Okay. So usually I'm going to present those output of set scan later. So usually it will have the summary of the results and to show the number of the clusters, the location information. Now what's the location within of each clusters? The risk estimate for each of the location, and the log likelihood ratio test. And then we can it also generates the shape file, and those shape file can be imported into any of the GIS software to make the map plot, Okay. So again, and the set scan is conducted by using cut-off type spatial scan statistic using this formula. So basically, we need to have C with observed count, and then we can have the expected value for the cases. The expected value for the cases can be calculated outside of the set scan. For example, we can use like a SAS or R to calculate the predicted value for a Poisson model and aggregate those predicted value by the county or sensor tractor, and import those expected value in set scan to conduct spatial test for that. Okay, so here is the example of the Massachusetts map data for the most likely clusters. Okay, and I would like to use a real data to show how do we find out the clustering of the breast cancer, and by using the Massachusetts Cancer Research data, which is most recent year data, which is from 2004 to 2013. Okay, so by using this and the Massachusetts Cancer Research data, we'll try to identify the breast cancer, the high and the low, and the incidences of the breast cancer over those 10-year period. And we can also compare our results with earlier study, which is in the Xinhan's paper. They study the breast cancer, the spatial distribution of the breast cancer also for Massachusetts, but for the early 10 years from 1988 to 1997. Okay, So here we need to combine those two data sets together. One is Massachusetts cancer registry data, and then the other is the census breast data. Okay, for the MCR data here, we have the cancer information, and here we also have the age. The cancer happened by age, and by zip code, and by census tract here. Okay, and we also know the year, we know the race, and the type of the cancer. Okay, so for this study, we just make selection of the breast cancer. Okay, now, and since we need to control for the population by age, so we need to have another data set from the census data, and we don't know a census data by county code and by census tract, and then the two data sets are merged by county and the census tract in order to get information of the population of the female population by age group, and then we also need to know additional information, for example, like median income, like like urban and rural status here to control for that. So here are the descriptive statistics. Okay, so for the cancer data here, for over the 10 years, there were 68,643 breast cancer, but unfortunately, there are many of the missing, census tracts. Because these are real data, and some of the data, did not have the census tract. So so how do we do? Especially for later on, we're going to do analysis here for the non-Hispanic Black women, because the count is already quite small, so we don't want to miss those to reduce our sample size due to the missing of the census tract. So what we did is we randomly assign the census tract based on the zip code and the county code. This may not be accurate, but we try to keep the sample size as large as possible here. Okay. So the hypothesis assume those breast cancer follow a Poisson distribution with the same intensity rate over the entire study region of the Massachusetts. Okay, and then we use as I mentioned, it was the SARS ProGen model to calculate the expected count, and this expected count can be adjusted just by age and the population, and it can also be adjusted by the income and the urban and the rural status here. Okay, so the cluster are reported with the p-value less than 1%. And when we generate those output, and the output together with the map data can be imported into R or into other GIS software, and to make those map plot. Okay, now here is the outcome for the most likely cluster of the breast cancer for those 10 years here. Okay, now this is here I report 4 significant clusters, only 4 significant clusters, and with the relative risk, and with the likelihood ratio test. Those are observed count, those are expected counts here, and the p-value are all significant. Now, those 3 clusters, they are clustered but were not significant. Okay, if you check those p-value, they are greater than 5%, so they are not significant. Okay, so this is the output with 4 significant clusters. Here I only present 1 cluster here, and then with the number of the cases, and then this is observed the number of the cases you saw in the previous table, and those are expected number of the cases, and then relative cases p-value, and then relative cases, which is calculated based on this formula here. And then it also shows the most cluster region, and the location, and the size of the region here, the size of the region. So here, for the size of the region, and here are those locations are inside of the first cluster of the region here. This is output from Z-scan. Now, here we only present 4 of the significant cluster, and here we have additional 3 clusters which were not significant, but it can also, point out in the map area. Okay. Now here is the output of the clusters, of 5 clusters, and adjust for the income and urban lunar status here for the 10 years. And those are relative risk. Okay, those are 5 clusters were significant, and 2 of them were not significant. Yes. Okay. Now, in this map shows high and lower rate here. Okay. In the most of situation, we know the only one to test the high instance rate. Okay. We also want to know where are those lower instances. For example, in some of the area, if they have regular, if most of the people have the regular annual physical exam or have the mammogram, they may have lower breast cancer incidence rate here. So those blue circle represent the lower value of the relative risk here in the study area, in the study region. So here I list both high and the low relative risk here. These are quite low relative risk here, and with the significant p-values as well here. Okay. Now I will need to say that if we want to test both high and the lower rate, okay, so this issue, just like we need to perform 1-side or 2-side test, we rather to put the high and the lower rate together in one test. In that case, to keep the testing power. Otherwise, if we just test higher rate and then lower rate respectively, it will lose the testing power. So we rather to put the higher and the lower relative risk in one test to keep the high of the testing power here. Okay. Okay. So this is the, breast cancer incidence relative risk. Okay, age adjusted. This is only higher rate, and we put this in the map. Okay, and output those into the map data. Well, I still have 10 minutes here, and then this high and the lower rate into the map data here. And now this is also high and a lower rate, but adjust not only just for the age population, also adjust for the covariates of the median income and urban lunar status. And we input and we import the output from set scan into the map data to present it here. Okay, now this is the output for the non-Hispanic Black women. You can see that the counts are relatively small here, and then the clustering which was happened in 4 of the clusters here, 4 of the clusters here. Okay, and here is only adjusted for the age population, and with the both test high and lower relative risk here. Okay, now there is problem of use of the test of the relative risk test adjusted for the income for the non-Hispanic Black women. The reason is like that the income, the median income is for the zip code. It's for the census tracts. It's aggregated by the census tracts, but it's not for the Black women population. So this value, this median income for the Black women and all for the Black family need to be improved later on. Okay, so that's why this map look like the lower rate is for a quite large of the area if I adjust the relative risk for the income for the non-Hispanic Black women here. Okay. Okay, so here is the comparison of the value of the outcome of the spatial distribution of the breast cancer with the earlier data in Xinhan's paper. the shape is quite similar here, okay? So the distribution is quite similar, with the recent 10 year compared to earlier 10 year. So the higher relative risk is in the southeastern Massachusetts and the Cape Cod area, and the lower relative risk was in the Worcester County area, okay? And there is some change, okay, from earlier data to most recent data is the great area with higher relative risk in North Shore area here, okay. Some of the, high and low breast cancer incidences or relative risk could be explained by socioeconomic status and urban-rural status. Okay, so because there's lower relative risk in Western Massachusetts and the higher relative risk in North Shore area here. Okay, so there is limitation for this study, especially for the geocoding problem. There are quite amount of the missing of the geocode. There we need to, random assign those geocode, make it may not be accurate there. And then there are many of the non-reported counts here, especially in Western Massachusetts. The count, they are all 0 of the breast cancer. It doesn't mean they are really 0, but probably just due to no report. So we need to figure out those missing values there based on other resources of the data or other information. And then the other thing is for the inaccurate of the spatial model for the black women, for the non-Hispanic black women, is due to there are many 0 counts here. Okay, suppose yes, there are many of the 0 counts of the breast cancer there. We shall use the 0 inflect Poisson models. Okay, but not regular Poisson model because there are many of the too many of the 0 counts. So we shall apply the by using and the most recent study results to use the 0 inflect Poisson model, not just regular Poisson model, use the set scan here. Okay. So our conclusion is the spatial scan statistics, especially by set scan, can be used to examine breast cancer incidency in Massachusetts. Okay. Now observe the high and the low relative risk of breast cancer incidency can be affected by socioeconomic status or rural-urban status. Okay, so in that case, for the future study, we may need to find out additional covariates, explanatory variables. For example, if we have some additional the variables such as the percentage of the annual physical exam, mammogram rate, and there may be more socioeconomic variable like years of education and the median housing price or median the renting price, something like that. You may examine more of the spatial distribution of the breast cancer, may have some significance results, okay, in other areas there. Okay, so results showing today was only based on pure spatial scan statistics. We can certainly take the space-time model into consideration. Okay, so and then not for this data, but just in general, the set scan they can also test the spatial distribution. For the count data, it can also take the nominal data like normal distribution or normal distribution or exponential distribution into consideration. So that's possible of the other models there, okay? So there are all references for these seminars here, which some of the references I may not, explain very clearly, but, you can always check those references, especially those, Cutoff's early paper here. Okay, so thank you for attending this seminar, and I think we still have 2 minutes. Okay, I would like to ask questions. If you have any questions regarding to the spatial scan statistic using set scan for breast cancer incidences. Any questions for that? No? Thank you for coming. Yeah.